Okay, so simple subsequences. So you can probably guess what a subsequence is, right? You have some sequence, piece of n, right? And then a subsequence is just a selection of elements of that sequence. So the way you write it down formally is if you have n sub k from 1 to infinity, and a strictly increasing sequence of natural numbers, then anything like then we call p sub n sub k, k from 1 to infinity, a subsequence of p sub n. So that's sort of right. So anything that looks like this is called is a subsequence. Okay. Right. Does everybody okay with this definition? Right. You have some sequence to start off with: p1, p2, p3, p4, p5, etc. Right. And all it's saying is that you're choosing some of those indices. Those indices are strictly increasing, and the elements that correspond to those increasing indices that you've selected are a subsequence. Does that make sense? Yeah, Jonah.
Does k have to go from 1 to infinity?
Yeah. We want to have an infinite sequence. Yeah. Mia, your brow is slightly knit. Is anything?
Yeah, I think my question was similar. Just, I'm a little bit confused with, we're only taking like some selections. So like concretely, like if you were taking like 2, 4, 5.
Yeah, so that would be our n sub k sequence, right? N1 would be 2, right? You
would say like
N1 is 2,
equals 2.
N2 is 4, N3 is 5, etc. Right? So you're taking a strictly increasing sequence, but you're not necessarily taking every element. You're not taking 1, 2, 3. You're taking some. Yeah, there could be some gaps in it.
But all subsequences are infinite.
Yeah, all subsequences. And so anything that looks like this, we call a subsequence. So choosing a subsequence corresponds to choosing a sequence of increasing indices. Okay. Maybe this is clear. P sub n converges to some point p if and only if every subsequence converges to p. Okay, so going backwards is easy, right? If every subsequence converges to p, then certainly the full sequence converges to p, because you just choose the subsequence that is the full sequence, right? The full sequence could be considered a subsequence of itself. Okay, so you just say, well, if every subsequence converges to p, well then the sequence itself is a subsequence of itself, so it converges to p also, right? And then going forwards, right? Suppose that say p sub n converges to p, right? Then so choose some arbitrary. Say p sub n sub k is a subsequence of p sub n, and you want to show that P and K converges to P, right? In other words, that given any epsilon, there exists some number n such that if K exceeds n, then the distance from P and K to P is smaller than epsilon. Okay. Take 30 seconds or take a minute and see if you can write down how you would choose that. How would you choose that n? Okay. You know that P sub n converges to P. You're trying to show that P sub n sub k converges to P. Okay. So think about it for a minute and see if you can say something, you understand it intuitively, and if you do, write it down. Okay, turn to somebody nearby and say, it makes sense because, you know, such and such a reason.
Yeah, so basically you can find a big
Yeah, the weird part is that
same as one P together.
one that could be C2.
Original sequence.
That's what he's saying.
Oh, yeah.
So like this one is not the same case,
Yeah.
which makes it. But if you put some n in here,
Yeah,
such that any P so n greater than that n, it's going to be less than epsilon. If you make that epsilon, somehow you're talking.
Well, that K is.
Okay.
There is no
Okay. Would somebody like to explain the idea behind this? Right. So you know that the P sub n's converge to P, and you're trying to show that you have some subsequence. You fix some subsequence. You're trying to show that also converges to P. Right. So that what you have to do is you fix an epsilon and you say, well, I want to find an index for the subsequence so that everybody past that time for the subsequence is within epsilon of P, right? So what? Yeah, Jonah.
So you pick an epsilon that every n larger, okay, never mind, I already screwed up.
No,
You
so
have the right idea, though.
You have the right idea, so go on with your.
Essentially, you just want to pick a k
Yes.
that is indexed to any n that is larger than the n of that.
Exactly.
That's
exactly.
required for the epsilon.
Exactly. Very good. You pulled it off.
Good.
Good. Right. So you say, well, look, the epsilon is fixed, and you know that these guys converge to P, right? The original sequence converges to P. So for the original sequence, there's some point, like here it is, right? There's some point past which the original sequence, all the elements are within epsilon of P, right? So just choose your k so that the n sub k are all past that point, right? Choose your k so that the n sub k are all past that point. You say, okay, we know. Since P sub n converges to P, there exists some value. There exists some time. I use something else. T, such that if n is bigger than t, then p sub n, the distance of p sub n from t is smaller than epsilon, right? Okay, well, the n sub k are increasing. So choose k such that, I'm sorry, choose n such that k bigger than n implies that n sub k is bigger than t. Right? Choose your n so that k bigger than n implies n sub k is bigger than t. Then k bigger than n implies that p sub n k, the distance of p sub n from k is smaller than epsilon, right? Because n sub k is bigger than t. Okay, right. So the intuition I think is clear, right? You know, you just say, well, look, there's this time. Make sure that you're past that time, right? And then it's just a matter of writing it down. Okay. I think half of the problem is writing things down. You know, you've got the idea, you know, writing it down in a coherent, you know, manner. Okay. Any questions? Any questions so far? Okay. Okay. So okay. Second fact about subsequences. So you have p sub n, a sequence in a metric space X. Okay. If X is compact, then some subsequence of p sub n converges in X. Okay. So if the space is compact, then you're guaranteed a convergent subsequence. Okay, so for example, as a corollary, in Rn, any bounded sequence has a convergent subsequence. Right? Right? Why? Because if you're bounded, then you're sitting inside of a compact set, right? If you're bounded, you're inside some ball. Make sure that the ball is closed, and then it's a compact set. You close the ball. If it's not closed, close it. Then you have a compact set. So you have a sequence inside a compact set, and have a convergent subsequence. Okay, right? Of course, bounded doesn't imply convergent in general, right? You could have some sequence like p sub n is -1 to the n, right? It's bounded, but doesn't converge, right? But you see that this one has a convergent subsequence, namely the even terms or the odd terms. Okay, so why is this true? If you're compact, then you have some convergent subsequence. You have a sequence, right? Your set is compact. You have an infinite sequence. You have an infinite sequence in there, right? Why are you guaranteed a convergent subsequence? So.
You just keep taking smaller and smaller k cells until you get a finite number of terms that converge to a smaller number.
So remember, first off, we're not we're not necessarily in Rn. Okay, we're just in some compact metric space. But does anyone have an idea? Okay, so you can split it up into two possibilities. Consider the range of p sub n. Right, p sub n you think of as a function on the natural numbers. Right, look at the image. Look at the image of this function. If the range is finite. Suppose the range is finite. Okay. Suppose the range is finite. So, like this example here, p sub n being -1 to the n. Right. The range has only 2 values. Right. Then we were able to choose a convergent subsequence, right, by just choosing, you could take 1, 1, 1, 1, 1, 1, 1, 1, 1, right? Okay. Well, that's basically what you do in this case. If the range is finite, there may not be 2 values, but there's some finite number of values, right? And then you play exactly the same. You do exactly the same thing, right? So you say, well, look, suppose the range is finite. Say it's R1 to Rk. Then one of these values must be obtained infinitely many times. Right? Does that make sense? One of those values, it's the pigeonhole principle, right? You have k pigeons, right? You've got, you've got k holes, excuse me. You got k holes, and you've got an infinite number of pigeons. Well, one of those holes has to contain infinitely many pigeons. Otherwise, there's only finitely many pigeons. Okay. Okay. So one of these values must have been hit infinitely many times. So you say, okay, just let n sub k, let n sub j be the indices such that in increasing order such that p sub n sub k equals that value. Let's say one of these values, say R1, say, must have been hit infinitely many times. Well, just choose all the indices where you attain that value, and then that will be your convergent sequence because it's a constant sequence. Any questions about that? Alex, do you have a question? No. Okay. Okay. Well, so that's one possibility. 2, suppose the range is infinite. Well, in that case, you have you have infinitely many different points sitting inside a compact set, right? Well, what do you know about that? If you have a compact set and you have an infinite subset, right? You have an infinite subset in that compact set. There's something we know about it? There's a limit point, right? There's a limit point. Then by previous theorem, there exists a limit point P, right, in X. Right. And then you just construct your, right? Remember, call every given any epsilon, the punctured epsilon neighborhood around P contains infinitely many points. Right? And so you can construct your sequence by using that fact, right? You say, well, take epsilon to be 1. Then by the above, there exists some piece of n sub 1 that lies right, in n1p. Right. And then, for your second epsilon, you just take the distance. You take the distance from Pn sub 1 to P, right? And then let epsilon 2 be the distance from Pn1 to P. Then there exists Pn2 that lies in P epsilon 2, right? And so on and so forth. Okay, there's actually something wrong with that, right? Does anyone see what's wrong with that? Hold on for 1 second. So there's something wrong with this proof. It's not terribly wrong, but it's wrong. Okay, go ahead, Adam. What is it?
There's no guarantee that it's ordered correctly.
Yeah, that's the trouble, right? So my n2 might not be bigger than n1, right? But that's easy enough to get around, right? Because so if I were clumsy, so first thing I did was I took an epsilon of 1, and I said, okay, there's somebody in here. Let's call that guy Pn1. Right, and then I took this as my epsilon, and I said, there's somebody in here, that guy's going to be, let's call that guy Pn2. But who knows, maybe that index is actually smaller than n1, and so I'm not making a sequence here, right? But if that happens, then I'm just not going to use that guy, right? There's infinitely many other points inside here, so there's definitely one whose index is bigger than n1. Okay, so just but just note that you just say since we can choose n2 so that n2 is bigger than n1, since there are infinitely many of them, infinitely many Pn in that E2 neighborhood. Right. It was just a bad, we'd have just made a bad choice. Okay, so you just need to note that. And then so on and so forth, etc. So, yeah. Okay. Okay, any questions? I realized when I got into class that I was feeling kind of down. You all look kind of down yourselves, but I was feeling kind of down. But you may have noticed that I started smiling at some point. And this is because I realized why I was down. And it's because yesterday at my son's 6th birthday party, I was beaten by some other parents in a game. So I realized that was probably why I was feeling down.
What game?
Blockus. Blockus, like a kid's game. Yes, Joanna.
So why is Pn closed? Subset of X. So let's say there exists at any point P in X. Are we assuming that Pn is a closed subset of X?
No.
I thought the previous theorem is like if some.
No, you just need an infinite subset of a compact set.
Oh, okay.
Yeah. So that's why we wanted to get rid of the finite case in order to say that we have the infinite case here.
Did the rest of the party go well?
That just ruined it. You know? No, actually, that was, I think, the end of the party. Yeah. Yeah. Okay. Okay. Next thing is the very important notion of Cauchy sequence. Can anyone tell me what a Cauchy sequence is? Anybody know? So it's a little bit different from a convergent sequence. Anyone read it? Fernando, go ahead.
So for any given epsilon greater than 0, there exists some n such that for n and m, lowercase n and m greater than n, we have the distance between p of n and p of n less than epsilon.
So it's different from convergent, right, in the sense that we're not saying that we don't mention what it's converging to, right? For the definition of a convergent sequence, you say there's some point P, and everybody gets within epsilon of P. And here what we're saying is that we can make, it's not that we can make them close to some point, but that we can make terms close to each other. Okay. There's some time past, given any distance, there's some time past which everybody is within that distance of each other. All points past that time are within epsilon of each other. Okay. And what we're going to see later on is, what we'll see later today is that in RK, sequence is Cauchy is convergent if and only if the sequence is Cauchy. But that's not always true. So convergent. What we'll see is that convergent always implies that you're Cauchy, but being Cauchy doesn't always imply that you're convergent. It depends on the space. For example, so this is not always true. For example, the same example we used before, 1.4, 1.41, 1.414, 1.4142, etc. That is a Cauchy sequence, right? That's a Cauchy sequence. If I want to make them, within, if I want to make these guys close to each other, it's clear enough how to do it. But in Q, this doesn't converge, right? In Q, so it is Cauchy, but doesn't converge in Q. Okay. So this is the notion of being Cauchy, right? You can control the distance between points. A nice concept that you can use to visualize this is the notion of a diameter. Okay, so diameter of a set. Okay, so let E be some subset of a metric space, and let S be the collection of all distances between pairs of points. Okay. Then we define the diameter of the set to be the supremum of all these pairwise distances. Okay, so it's the if you have some set, then this is your set E. Then the diameter is going to be the supremum of all pairwise distances, right? So like the largest distance you can get between 2 points in your set. So actually the least upper bound of those possible distances. Okay. Okay. So then. If we let, suppose we have some sequence, and we let E sub capital N be all the elements of your sequence past that point N. Okay. So this is the I think the tail of the sequence. So just you started at some point and you continue it onwards. Okay. Then P sub n is Cauchy is equivalent to saying that that the limit of the diameter of the tails as n goes to infinity is 0. it's exactly the statement, right? Does that make sense? Yes, Sam?
Why would it converge to 0 and not epsilon? Like just an epsilon period?
Well, because you're able to make it smaller than whatever epsilon you choose, right? To be Cauchy means that given any epsilon, we can find a point past which pairs are within epsilon of each other. So you can do that for 1, you can do that for 1/2, you can do that for 1/4, et cetera, right? So, is that clear? Is it clear that these two are exactly the same statement, right? You know, let's look at what this means. The limit of the diameter of the tails is 0, right? Translating that into epsilon language, it means that given any epsilon, there exists some n such that sorry, let me write this as little n. No, I'm going to write it as big N. There exists some m. Sorry, there exists some m such that if n is bigger than m, then the diameter of E sub n is smaller than epsilon. Right. That's what this second statement literally means. Right. Okay, right. But what does that mean? That's to say that the supremum of the distances between points P sub n, where n and m are bigger than n, is smaller than epsilon. Right? But if you look at the statement now, then that's exactly the definition of being a Cauchy sequence. Right? So it's exactly the same thing. Any questions? Any questions? Did anything happen this weekend that like anything exceedingly depressing happened this weekend? No? Okay, so Cauchy, right? Cauchy means that the diameter of the tail goes to 0. Okay, diameter of the tail goes to 0. Okay. A couple of facts about diameter that we're going to need. First, that the diameter of the closure of a set is the same thing as the diameter of the set itself. So when you close a set, don't change its diameter. Second, if you have a sequence of nested sets in X, and the Kn are all compact, and the limit of their diameters is 0, then their intersection consists of exactly one point. Okay. Can anyone tell me why this first one should be intuitively clear? Should be true? You have a set, you have the closure of the set, right? In other words, you throw in the limit points, right? And I'm saying that you don't change the diameter at all. You throw in the limit points. Why does that seem pretty clear? Alex?
Because since at a limit point, there's, for any size epsilon, there's a point E, and you can just take the small, the tiny epsilon of the radius or diameter would still be the same distance.
That's right, that's right. So, throwing in the limit points basically means that you're throwing in points that are infinitely close to your set, right? So throwing in these guys who are infinitely close to your set is not going to change the diameter, right? So let's write that out properly. You say, well, look, pick any 2 points P and Q in E bar. Okay. Well, since they're limit points, for any epsilon, we know that there exists P prime and Q prime in E, such that the distance from P to P prime is smaller than epsilon over 2, and the distance from Q to Q prime is smaller than epsilon over 2. Right. Is P and Q in E bar? Right. These guys are in E bar, but we choose any epsilon, we can find P prime and Q prime in E who are really close by, within epsilon over 2, right? So what you see is that the distance from P to Q, right, is less than or equal to the distance from P to P prime, plus the distance from P prime to Q prime, plus the distance from from Q prime to Q. Right, which is, that's to say, smaller than the distance from P prime to Q prime plus epsilon. Right, but that tells you that the diameter of E bar is smaller than the diameter of E plus epsilon. Right, for any epsilon. Right, and so that tells you that when you threw in the limit points, so when you threw in the limit points, you didn't increase the diameter. for part 2, we want to see that if you have a sequence of nested compact sets and the diameters go to 0, then the intersection must be a single point. Okay. So this should, some bells should be ringing when you see something like this, right? This reminds you of something we saw before. What do you know about the intersection? You have a bunch of compact sets. These guys are nested, even, right? They're nested, right? No, are you smiling? You're not really smiling. Okay, no. Okay. What does this remind you of? Something about compact sets? Non-empty, right? You have a bunch of compact sets that satisfy the finite intersection property, remember? Right? Any finite subcollection is non-empty, implies that the infinite intersection is non-empty. Okay. So, so we know that the intersection is non-empty. Okay. So the only thing we have to do is show that it can't have 2 points, right? Right, because it has at least 1 point, so we just have to show that it can't have 2 points. Suppose there are 2 points there. In the intersection. Well, then what? Then that's trouble, right? Why is that trouble? So?
Unless those 2 points are the same point, the distance between them is not 0.
Exactly.
So it has to be 0.
Yeah, right. If this were the case, then there's no way that our diameter could go down to 0, right? Because you'd always have these two different points in every one of the case of n would contain these 2 different points, so the diameter would be bigger than this distance, right? Bigger than or equal to this distance. Okay. So that's a contradiction. But then the diameter of case of n is bigger than some constant that's bigger than 0. For all n. Okay, is that all right? Everyone all right with that? Okay. Okay, so the next thing is something that I said earlier. Suppose that the piece of n be a sequence in some metric space X, as usual. Suppose you know that piece of n converges, then show that piece of n must be Cauchy. Okay, so being convergent implies that you're Cauchy, although being Cauchy does not imply that you're convergent. Okay, so can anyone think of why this is, think for a minute about why this is intuitively clear? Right. Being Cauchy means that you can control the size of the tail. Right. You can control the distance between points, between pairs of points. Right. Okay, go ahead, Mia.
Oh, did I look like I had an answer?
You were looking at me and nodding your head.
Oh.
Okay, forget it. No, do you want to? Okay, talk to somebody for half a minute and can make.
So that after we converge to sequence, the distance between that and what's converging to, the point P that's converging to is less than some epsilon. So then any 2 points beyond that n is going to also be less than epsilon. So you take any 2 points past that n, less than epsilon, so it's if you have,
And that's for any epsilon. So
like it's approaching this point P or something. If you pick like right here, this is your n. You pick any 2 points. And say that this then is your equal. Then any 2 points past that.
Okay. Okay. Would somebody like to say why this makes sense? Right. Convergent means that there's some point, and you can make these guys as close to the point as you want. Cauchy means that there's some time past which all pairs are within that distance of each other. Jonah, go ahead.
So you pick some n where some uppercase n where any n, like lowercase n of p is, the distance between that and the point to which it converges is less than is less than the epsilon at that n, the capital N. So then any 2 points, Pm and Pn, are going to be less than an epsilon as well.
Basically, but you're saying that so you fix an epsilon. Right, so fix. Fix epsilon, right, and then choose n such that since Pn converges to some point P, some point P, choose n such that n bigger than n implies that Pn's distance from P is smaller than epsilon.
Mm-hmm.
And then
Bring another point.
if n and m are bigger than n, then this is what you're saying, right? Then
Yeah,
the distance from
Pn and Pm is also less than epsilon.
that's not. I mean, it's sort of morally true, but it's not exactly true.
Okay.
It's less than.
For any given epsilon, choose the n that satisfies the distance p is smaller than epsilon over 2.
Epsilon over 2. Okay, so the trouble with what you said, Jonah, is that here's P, right, and here's the epsilon neighborhood, right? And you're saying, let's choose a time past which all of my guys are inside this epsilon neighborhood. So they're within epsilon of P, but they're not necessarily within epsilon of each other. They're within 2 epsilon of each other. Right? By the triangle inequality, what's the distance from here to here? It's smaller than this distance plus this distance, which is 2 epsilon. Right? So you just need to fix it up a little bit with the 2. But you had basically the right idea. Right? The point is that you can control the distance between these two guys. If you can control the distance between them and a point, you can control the distance between them and between each other. So yeah. Then by triangle inequality, the distance from P and Pm is less than or equal to the distance from P to Pn plus the distance from P to Pm, which is smaller than epsilon over 2 plus epsilon over 2. Okay, so being, like we said before, being convergent means that you're Cauchy. Being Cauchy does not imply that you're convergent. This leads to the following description. If you have a metric space, if every Cauchy sequence converges in X, we say X is complete. Okay, and what we're going to show right now is that our K Euclidean space is complete. So we do this in two parts. The first is to show that if X is a compact metric space, then X is complete. And the second is to show that that our K is complete. How do you think we're going to do the second part? RK is, of course, is not a compact metric space, but suppose we have some Cauchy sequence. Suppose you have some Cauchy sequence in Euclidean space. How are we going to use the first part to get the second part? Okay, let's see. It's going to be kind of similar to something we did earlier. Earlier we had this theorem. We said that if you have a bounded sequence in Euclidean space, then it's going to have a convergent subsequence, right? And the reason was if you're bounded, then you live inside of a compact set, right? Okay, so what are we going to do with this Cauchy sequence? Anyone have an idea? It's okay. If we could suppose we can show that the Cauchy sequence is bounded, right? Then it would be living inside of a compact metric space, right? And then we would just invoke part one, right? Okay. So is the Cauchy sequence bounded? Is the Cauchy sequence bounded?
Yes.
Yes. Why? Think about it, right? You have a sequence, and you can control the diameter of the tail, right? So control the diameter of the tail so that the diameter of the tail is smaller than 1. That means that all terms past a certain point live in a ball of radius 1, right? And then before then, you just have a finite number of terms, right? So you can certainly you can bound that finite number of terms in some gigantic ball, right? Just take the maximum of their distance from some fixed point, right? Okay, so it's bounded, and then RK is complete. Okay. Let's get let's do the first part. So say that say Pn is a Cauchy sequence, right? And let E sub n denote the tail as before. P sub n plus 1, P sub n plus 2, blah, 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 blah. Okay. 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 So now consider the closures of those E sub n's. take the set that makes up the tail and close that set. Okay, right. Right. We know that. What do we know about this sort of thing? What do we know?
The diameter will be the same.
Yeah, the diameters are the same, right? So certainly, right. So we know over here that remember that the limit of the diameters of the tails is 0 as n goes to infinity, right? Being Cauchy means that your tail, the diameters of your tail goes to 0, right? And so we know the same thing for this, right? The limit of the diameter of the closed tails also equal 0 as n goes to infinity. Okay. What else do we know? Well, these are, pretty good sets, right? What's good about them? They're closed. Are they bounded? Yeah, I guess they are bounded. Yep, they're closed and bounded. But we're not in our K, so you can't say by Heine-Borel they're compact. Okay, but close enough. They're closed, and our space is compact. Right? Our space is compact, so they're closed subsets of a compact set. So they're compact. Right? Any closed subset of a compact set is compact. So we don't need Heine-Borel. We just need the closure. Okay. So the E sub n are compact. And they're nested, right? By construction, they're nested, right? So by the previous theorem, we know that the intersection of the E sub n is a single point equals some point p in x. Right, and so we claim that the P sub n converge to that P. Right. The intersection of the closure of the tails is a single point, and we're going to claim that the sequence converges to that point P. Right. So, well, fix any epsilon. We have to find a time past which all the P sub n are within epsilon of P. Right? But that's straightforward, right? Because we know that the diameters of these tails is going to 0. Right? So just choose n such that if we're past that point, just choose m such that if we're past that point, then the diameter of E sub n closure is smaller than epsilon. And I'll just say epsilon over 2 just in case I need it. Okay. But then the distance from then if P sub n, then if little n is bigger than that capital N, the distance of P sub n to P is smaller than epsilon over 2. Smaller than smaller than epsilon. Actually, I don't need the epsilon over 2, so I'm just use epsilon. It's smaller than epsilon. Okay, so P and does converge to P. Okay, so any Cauchy sequence in a compact metric space converges, right? And that gives us that RK is complete. Do people want me to write down the proof that RK is complete, or was it sketched out clearly enough before? I'll just write it down. Give me a second. So proof of B. Let Pn be Cauchy in RK. There exists an n since the limit of the diameters of the E sub n is 0. We can choose n such that the diameter of E sub n is smaller than 1. Right. And these guys are shrinking. These guys are shrinking. Wait until they're smaller than diameter 1. But then, the distance between, right? So then the distance between Pn and Pm is smaller than 1 for all n bigger than n. Right. And so E sub n is a bounded set. Right, the tail is bounded. And then further, P1 through Pn minus 1 is also bounded because it's finite. Right? And so you know that so being Cauchy implies that you're bounded. Being Cauchy implies that you're bounded. And so and then you just argue as before, right? You've got a bounded set, so it's living inside of a compact metric space, and so you know that your Cauchy sequence has to converge. So Euclidean space is complete. Okay, I hope you all cheer up before next time. I'm going to hand back the homeworks.